Hello and welcome back to a new video. In this one we're going to be covering the spectral action for the Standard Model minimally coupled to gravity. This will be about how the laws of physics emerge from pure geometry. So what is our main idea? A common discussion on modern physics will often correspond to an inevitable conclusion. Our fundamental laws of physics generally come down to two equations that stem from seemingly distinct field theories, one of the classical gravitational field and another of quantum fields, composing what's called the Standard Model of particle physics. The field equation describing the gravitational field relies on space-time curvature of a pseudo-Riemannian manifold. This study is contained within classical field theory, and the fundamental equation of interest is called Einstein's field equation of general relativity, taking the following tensorial component form. We have the Ricci curvature tensor components R sub mu nu minus 1/2 the Ricci curvature scalar times the metric tensor components G sub mu nu plus the cosmological constant times the metric tensor components equals 8 pi g divided by c to the 4th power times the energy momentum tensor components, showing the relationship between energy and curvature. Meanwhile, the equation describing the Standard Model of particle physics is given by a Lagrangian density. The first sector, the Dirac sector, is given by the Dirac conjugate of spinor fields multiplied into I times h bar times the Dirac operator acting on the spinor fields, minus 1/4 the collection of Yang-Mills tensor fields, F upper mu nu with F sub mu nu, minus the Dirac conjugate of spinor fields times the Yukawa mixing matrix in terms of left and right-handed fermion particles acting then also on the Higgs field, coupled then with spinor fields, plus the kinetic term for the Higgs field, which is the covariant derivative of the Higgs field, its norm squared minus the potential of the Higgs field via phi. In order to encode both of these theories, we want to consider which mathematical objects we wish to use that encompass the algebras, operators, symmetries, and derivations that are found within the Einstein field equation as well as the Standard Model Lagrangian. In non-commutative geometry, we rely on a geometric invariant called a spectral triple to begin organizing the information we need to encode these field theories. The 5 key ingredients mentioned above can be contained in a spectral triple A, H, D, J, and gamma, where A, H, and D are the primary operators that remain invariant and constant throughout all spectral triples, with J and gamma being additions, and this all unifies to what we need into a single geometric object. A is an operator algebra on a manifold M. H is a Hilbert space. D is a self-adjoint differential operator which encodes the information of a metric G on a manifold M. J is a charge conjugation operator, and gamma is a gamma matrix, identifying as a chirality operator within this specific context. Now we must consider which algebra, Hilbert space, and derivation operator from the spectral triple we need to encode the aforementioned classical and quantum field theories. For general relativity, our work is relatively simple in regards to determining an appropriate algebra, as we can indeed rely on the space of infinitely differentiable functions on a pseudo-Riemannian manifold denoted C infinity of M. The Standard Model, however, requires a bit more consideration. Consider, for example, the Yang-Mills Lie group manifold G for the Standard Model, given by SU3 cross SU2 cross U1. If the exponential map plays the role of mapping elements of a Lie algebra to a Lie group, then the logarithmic map plays the role of mapping elements of the Lie group to the algebra. So the logarithmic map over all elements of the Lie group G yields the tangent space at the identity element of that group, and this tangent space is the Lie algebra little g. This is given by a direct sum SU3 plus SU2 plus U1 as an algebra. To encode the symmetries of the Standard Model, it seems that we will need a non-commutative finite associative algebra that, when tensored with C infinity of M, gives us the full operator algebra A we need to encode all the gauge symmetries of known physics. We can encode U1 with the field of complex numbers C, forming a commutative algebra featuring also a trivial derivation algebra. We can then encode SU2 using the field of quaternions, denoted by H, and this forms a non-commutative algebra featuring a non-trivial derivation algebra. It is in fact isomorphic to SO3, and by proxy it is isomorphic to SU2. We can encode SU3 using the set of rank 3 complex matrices M sub 3C, forming a non-commutative algebra that likewise features a non-trivial derivation algebra isomorphic to GL3C. The traceless part of GL3C is SL3C, the special linear algebra, which is the complexification of SU3. Alas, the direct sum of these three algebras forms the non-commutative finite associative algebra we need to encode the entire Lie group SU3 cross SU2 cross U1. Our entire operator algebra then takes the following form. We have the tensor product formed by the C infinity of M with C plus H plus M sub 3C. Our Hilbert space, which is where our algebra acts, must be defined with a spinor bundle on the pseudo-Riemannian manifold, in which to encode fermions onto a curved manifold, as well as including the internal degrees of freedom necessary for particle generations, chirality, etc. The space of square integrable functions with a spinor bundle S on the manifold, tensored with the finite degrees of freedom of fermionic Hilbert spaces, forms a tensor product space, yielding the total Hilbert space we need. So L2 of M and S is the space of square integrable functions with the spinor bundle S on the manifold, and it is tensored with this fermionic Hilbert space degrees of freedom. We can split it up between left-handed particles and right-handed particles. The sum of left-handed and right-handed fermions include all quarks, that being the up, down, charm, strange, top, and bottom quarks. It includes all charged leptons, and that of course includes the electrons, muons, and tau particles, as well as all the neutrinos corresponding to the uncharged leptons. These fermion state spaces can be further decomposed into matter and antimatter subspaces. We can split this up further. So we have plus and minus charges for left and right-handed particles, giving us 4 different state spaces, which can then decompose even further between the leptons and quarks. A quantum state psi, which is an element of the Hilbert space, is given by a discrete sum over spinor field psi sub k of x in the space of square integrable functions on the Riemannian manifold with an attached spinor bundle, and this is tensored with the basis elements E sub k in the finite fermionic degrees of freedom Hilbert spaces that are corresponding to each of the fermionic states. So psi is equal to the sum over all k of psi sub k of x tensored with E sub k. So this is our operator algebra, and we also have our Hilbert space. So with this algebra and Hilbert space, we now want to consider which self-adjoint differential operator we wish to use. We want to start by considering 2 parts of the Dirac operator, one which operates on the Hilbert space over the manifold M to encode gravity, and another which encodes the finite internal degrees of freedom of the standard model. This will be the geometric part of the Dirac operator acting trivially on the Hilbert space through the tensoring of the identity element, plus the chirality operator tensored with the fermionic internal degrees of freedom of the Dirac operator. Now normally we would have a covariant derivative acting on gamma matrices, with both spin derivative connection coefficients as well as gauge derivative connection coefficients. The geometric part features a density of matrices. In this case, it includes rho, which then includes fermionic masses, and including neutrinos if necessary, as well as CKM mixing parameters. But there is a catch with that gauge term in the Dirac operator. It goes to 0. Since the Dirac operator is enhanced by its assignment within the spectral triple we've already defined, where gauge symmetries are naturally encoded within an operator algebra acting in the modified Hilbert space shown prior, we don't need to write out the term IQ A sub mu at all. This term becomes redundant as gauge fields emerge from inner fluctuations of the Dirac operator. And these fluctuations are called inner because they come from within the operator algebra we decided upon in the first place. This feature is a particularly unique aspect of non-commutative geometry. Gauge symmetries are inherited from degrees of freedom made available by the algebra, meaning we do not need to impose them externally. The Dirac operator that we need relies only on a spin covariant connection for the spinor bundle over the manifold in the Hilbert space. The full spectral triple AH and D for the standard model coupled to gravity, where for now we ignore charge conjugation in particular, is given by the following. Bringing in the charge conjugation operator J, where the chirality operator gamma 5 is already defined in the Dirac operator, our spectral triple AH, D, and J allows us to summarize all of general relativity, quantum field theory, and more within a single geometric invariant. And if we allow f to be a cutoff function, which can be a smooth approximation of the characteristic function of the interval 0 lambda, where lambda is a Planck-valued cutoff scale, the action functional S, otherwise known as the spectral action, can be written as follows. We have the trace of f of d slash lambda plus 1/2 the inner product of d psi and j psi. The trace term gives us gravity and gauge fields, whereas the inner product term gives us fermion fields as well as Yukawa coupling terms. The trace term generates Einstein-Yang-Mills theory, where we can neglect chirality and focus only on non-negative eigenvalues of the Dirac operator, making our ability to study this term much easier. As such, the trace term is often written in the following form. We can examine the squared Dirac operator in local form by first considering the first order original Dirac operator with a spin connection, forging a spin covariant derivative. Once again, we emphasize the lack of a gauge connection. Letting A be a self-adjoint operator from the algebra A equals A sub m cross A sub f, gauge connections emerge from the following inner fluctuations of the Dirac operator. We can now square the operator to yield the following. This was covered in my prior video over derivatives. The commutators for the gamma matrices give us 2 times the inverse metric tensor. Meanwhile, the commutators for the covariant derivative components gives us 1/4 the Riemann curvature tensor components acting on the gamma matrices. It is clear from the commutators that the squared Dirac operator alone is sufficient for a spin representation of curvature, and this becomes particularly useful for an asymptotic expansion of our trace term, which we will indeed cover later. For a flat 4D spacetime without the presence of the Higgs field, the trace term can be represented in integral form as a Yang-Mills action. So we have 1/4 the integral over the manifold of the Yang-Mills Lagrangian integrated over spacetime. For a curved spacetime, the Einstein-Yang-Mills action is then given by the following. Recalling here that G is the determinant of the metric tensor. With the presence of the Higgs field that emerges from inner fluctuations of the Dirac operator, we then obtain the Einstein-Yang-Mills Higgs action, describing the full gravitational and bosonic aspects of the trace term relevant to modern physics. Since the fermion and Yukawa part is an inner product, we can write out the entire spectral action explicitly in integral form. Let's write out that inner product form of the Dirac operator acting on spinor fields in terms of its Lagrangian. It's already in Lagrangian form, but we're going to write that out explicitly to justify why we're combining this into one integral over a space-time manifold. We can find the expectation value of an observable O over all field configurations by exponentiating the spectral action, multiplying that by the observable, and integrating in respect to the functional measures of each field, with a factor of a partition function for normalization. By setting the observable to the identity operator 1, we obtain the total probability of all possible field configurations. Knowing that the total probability must be equal to 1, we then know that the partition function z must be equal to the path integral. This is the general form of the Feynman path integral for all fields. Unfortunately, the gravitational sector is indeed non-renormalizable, as we obtain divergences that cannot be countered with a finite number of terms. Though, as we will see, this won't remain a problem under the purview of non-commutative geometry. So how could we possibly resolve the normalization crisis that just emerged in that theory? Simple. We just don't try to renormalize gravity in the first place. Instead, we consider another approach entirely. What if, for example, quantum fields are just correction terms for gravity? Recall in our trace term that we included a cutoff function and a scaling term. These terms are key to avoiding the renormalization issue altogether. We can expand the trace term as a discrete sum of Seeley-DeWitt coefficients acting on the squared Dirac operator, recalling that the Seeley-DeWitt coefficients are integrals of geometric invariance. For a 4D spacetime, our expansion takes the following form. We have the sum, as k ranges from 0 to infinity, of our scaling term lambda to the power of 4 minus k times the Seeley-DeWitt coefficients a sub k acting on the squared Dirac operator times the moments of the cutoff function f sub 4 minus k. In an even-dimensional spacetime, such as the one we are interested in, all expansion terms go to 0 since odd values of the Seeley-DeWitt coefficients a sub k acting on the squared Dirac operator produce odd numbers of derivatives and/or curvature tensors. And integrating geometric objects with odd parity over the entire manifold yields 0 due to its symmetry. So here we are left with the even terms written out explicitly. Each sector corresponds to fundamental field theories within physics. The a sub 0 sector acting on d squared correlates to the cosmological constant term, and it has the heaviest scaling factor, lambda to the fourth, as a dominant term of the series. This corresponds to the intrinsic energy and volume of a spacetime manifold. We sometimes refer to this as the cosmological constant term. A sub 2 acting on d squared correlates to the Einstein-Hilbert action, and it likewise features a Heving scaling term, lambda squared. It emerges immediately after the establishment of intrinsic space-time energy. So we also want to weight this to ensure that we do not try to renormalize gravity within a quantum regime. This equation here, of course, leads back to the Einstein field equation of general relativity. While higher order terms beyond a sub 4 certainly exist, we only really need the addition of the a sub 4 sector to obtain the rest of the inner fluctuations for what we need for Yang-Mills, e.g. strong nuclear and electroweak fields, and the Higgs field. So the trace of the Yang-Mills field tensor components are going to give you those Yang-Mills fields, as well as the addition. In this case, we have the kinetic and potential terms of the Higgs field, all being multiplied by the square root of negative g and integrated over the space-time manifold. In other words, we really only need the first three even terms to represent everything we need for gravity and boson fields, eliminating the need of an infinite series altogether. Notice that the term a sub 4 acting on the squared Dirac operator containing the Yang-Mills Higgs sector has a scaling coefficient that cancels to the identity. These are terms corresponding to inner fluctuations of the Dirac operator, which add correction terms to our curvature as we expand beyond the first two even terms. So let's go ahead and get rid of that. Just continue simplifying one step at a time. It is important that we retain lambda within the two terms for gravity, as we want to scale that off to make sure that we don't go into the high energy regime of the Planck scale. The eigenvalues in our non-commutative theory are square root dependent, meaning that we need to be careful when choosing the Mellin transform we need for determining the value of our cutoff function f, where f sub 4 minus k, as we have mentioned prior, are moments of this cutoff function. The Mellin transform of a function f of u for a complex variable s is given by the definite integral ranging from 0 to infinity of f of u times u to the s minus 1 integrated in respect to u. So it turns out that we're really left with answering two questions. One, which f of u ensures that our integral rapidly converges and in the process exponentially dampens higher eigenvalues of the Dirac operator? And two, which value s ensures that we even respect the square root dependence of these eigenvalues in the first place? Let's answer that first question. An exponential decay function e to the negative u may seem like an obvious choice, and that turns out to work just fine, as this allows us to express the Mellin transform as a gamma function. So by choosing the decay function e to the negative u, we get the integral ranging from 0 to infinity of e to the negative u times u to the s minus 1 du, and this equals the gamma function evaluated at the complex variable s. Now, which value s ensures that we respect the square root dependence of these eigenvalues? While choosing s to be 4 minus k, or even 3 minus k to contend with a factor of minus 1 that's in our gamma function definition, might seem natural, this selection gives us issues with the square root dependent eigenvalues. So instead, we choose to sum over half integer powers, yielding the following Mellin transform. So we're left with the gamma function evaluated at 4 minus k over 2, all plus 1. Our moments f sub 4 minus k can be computed by plugging in values of k directly into the gamma function. So for f sub 4 minus k, we get the gamma function of 4 minus k over 2 plus 1, and so for our expanded trace term, we get the following construction. F sub 4 is equal to f sub 4 minus 0, yielding the gamma function evaluated at 3. F sub 2 is then the gamma function evaluated at 2. and then f sub 0 is the gamma function evaluated at 1. We can then replace the moments of the cutoff function with their corresponding gamma functions. The gamma functions simplify further due to the fact that they are all of positive integer value, meaning that they are all special cases of the factorial function. Specifically k minus 1 factorial for all k that are elements of the natural numbers. So gamma of 3 is equal to 2. Gamma of 2 is equal to 1, as well as gamma of 1. This gives us neatly organized form for all of our terms in the heat kernel expansion. Now we can set the scaling factor to the Planck mass itself. A fascinating coincidence occurs for the Einstein-Hilbert sector in A sub 2, and this is due to the inherent structure of Einstein's gravitational coupling constant kappa, which depends on Newton's gravitational constant g. Namely, if the squared Planck mass is equal to h bar c divided by g, then this implies that Newton's gravitational constant is equal to the reduced Planck constant times the speed of light divided by the squared Planck mass. So kappa itself can then be written in terms of 8 pi times the reduced Planck constant divided by c to the third times the squared Planck mass. By adding the fermion and Yukawa inner product back into the picture, we can encode all known principles of physics by this collection of geometric data. Emphasis on known principles of physics. We'll write this integral in terms of a Hilbert trace. And then recall that we also have the Hilbert trace to generate these first 3 terms in our series in the first place. So we have a sum of 2 Hilbert traces. We just commonly write the Hilbert trace of the Dirac area as an inner product, often with a normalization factor of 1/2, depending on what aspect of the theory you're wanting to work on and what energies you're interested in. But just like that, we have formulated all known physics from purely geometric spectral data. The Lagrangian density for the standard model, which is minimally coupled to gravity, can then be expressed as the following. The Glashow-Weinberg-Salam sector, in addition to the strong couplings, or in this case, together the full standard model without gravity, will be expanded on the next slide. This is something I wrote down on a whiteboard quite a while ago. If you really want to see these terms, I implore you to pause this video. We can write these in terms of their explicit Lagrangian formulations and their dependencies, or just write them as the Lagrangian density sums directly without their dependencies, as long as we know what we're talking about. This is Dirac, Yang-Mills, Yukawa, Higgs, and Einstein-Hilbert-de Sitter Lagrangian sums. And that is then the sum of the standard model Lagrangian with the Einstein-Hilbert-de Sitter Lagrangian. To bring this back around, we integrate the Lagrangian density over spacetime, while multiplying through by the square root of the negative determinant of the metric tensor as we do so to form the spectral stationary action. And we have been brought around full circle here. So given a spectral action S, its variation equals 0. This fundamentally composes all of modern physics. We will expand by one more even term to see an example of where regularization is immediately needed. We focus on f sub minus 2. Recalling the definition of the moments of our cutoff function in terms of the gamma function. So f sub minus 2 is indeed a divergent term because gamma of 0 is undefined. To resolve the singularity of the gamma function evaluated at 0, however, we can consider the Laurent series expansion of the gamma function around z equals 0. So gamma of z can be Laurent series expanded around z equals 0 to yield 1 over z, the divergent part, minus the Euler-Mascheroni constant plus this sum from n goes 1 to infinity of negative 1 to the n times the Riemann zeta function of n plus 1 divided by n factorial times z to the n. So we end up with 1 over z minus the Euler-Mascheroni constant minus the Riemann zeta function evaluated at 2 times z plus 1/2 the zeta function evaluated at 3 times z squared minus 1/6 the Riemann zeta function evaluated at 4 times z cubed plus etc. etc. Where for every z to the n we get a factor of gamma of n plus 1. This evaluates to 1 over z minus gamma minus pi squared over 6 times z plus 1 over 2 times a Paris constant times z squared minus pi to the 4th over 540 times z cubed plus etc. etc. Let's contain all orders of z and higher in big O notation. We can then subtract the divergent part from the gamma function of z to yield the following. Now we take the limit as z approaches 0. On the right-hand side, minus the Euler-Mascheroni constant comes out of the limit since it does not depend on z whatsoever. And then in big O notation, the z terms of order 1 and higher all go to 0 under the limit, yielding the regularized gamma function evaluated at 0. And that gives us minus the Euler-Mascheroni constant. Writing out the A sub 6 sector is an extremely arduous task, as it includes combinations of endomorphisms acting on sections of the vector bundle, as well as all possible combinations of the Ricci scalar R, the Ricci tensor components R sub mu nu, the Riemann curvature tensor components R sub mu nu sigma lambda, and covariant derivatives of each of these combinations all up to 4th order. In total, over 100 terms can be yielded from this sector alone. But thankfully, higher order terms beyond A sub 4 contribute negligibly to the physical quantities until we reach absurdly high energies at the Planck scale. This corresponds to the inverse scaling factor. We can take another approach to estimate the complexity of quantum gravity at the one-loop level by considering the correction terms generated by the A sub 6 sector. The one-loop effective action gamma 1 for a field operator D is then given by a definite time integral. The heat kernel expansion of e to the negative Td is then given by a sum over Seeley-DeWitt coefficients acting on the field operator. This can be rewritten in terms of an integral over the manifold of the trace of the heat kernel in respect to this measure. The heat kernel can then be expanded as follows. Now this seems like a lot now, so let's break down the new terms we see here. Sigma of x and x prime is Singe's world function, encoding the geodesic distance between 2 points. Delta of x and x prime is a Van Vleck-Moret determinant, a scalar function measuring the deviation of geodesics. Omega sub k of x and x prime are Hadamard-DeWitt coefficients, which are recursively defined tensorial functions encoding the effects of curvature on field propagations. With this information, we evaluate A sub 6 under a general form. The sum over Q sub I contains combinations of an endomorphism E, curvature tensors, and covariant derivatives for each combination. This is what generates the overwhelming amount of terms for the one-loop effective action of the A sub 6 sector, showing us a calculation for which there exists no collection of supercomputing power on our planet that is remotely sufficient for accurate calculations of this term. The combinatorial methods alone that are required to organize this information at a tensorial level exceeds the memory limitations of our best supercomputers combined, let alone the methods that would be required for analytical or numerical solutions once combinatoric manipulation of tensors is set aside. The quest to resolve the problem of further corrections just one step beyond A sub 4 for quantum gravity, even at just the one loop level, assuming such a theory begs to exist, is likely proportional to how tough it would be to master this sector we have described, making it effectively unfeasible given our current technological limitations. We will ignore for now the fact that there exist infinitely more correction terms, though less contributory, by nature of asymptotic expansion. In other words, there are potentially an infinite number of correction terms that may contribute to physics that we will never be able to attain in a finite number of lifetimes, so long as we continue this path of concerning ourselves with higher energy physics. If the infinite series shown is any hint, then whatever corrections exist to gravity beyond what we currently use to describe it are leaps and bounds more complicated than our current best theory of gravity. In fact, the magnitude of difference between the complexity of the Einstein-Hilbert action and the A sub 6 sector alone is far greater than the leap from understanding basic arithmetic to deriving from scratch everything we have covered up to A sub 4, which contains all of known physics. But if going from basic arithmetic to general relativity or even all of known physics through the standard model with general relativity, if that is then considered an additive linear sequential progression along a slope, then going from general relativity or the standard model to A sub 6 is like an exponential, nonlinear, and non-sequential hike along a superposition of paths. So what exactly is quantum gravity, and how should we expect to go about even determining what it is if we don't already currently know, which we certainly don't? Well, I don't pretend to have an answer, but I implore you to think about it nonetheless. Is it the quantization of space-time? Is it the act of making quantum fields classical? In other words, is it composed of quantum or classical graviton fields? Is it perhaps a geometric invariant for which classical spacetime and quantum fields just emerge as unique theories, such as, for example, how perhaps classical and quantum fields might be dual to each other as byproducts of a statistical ensemble forged by some type of geometric invariant, such as what we covered in this video? No human in existence actually knows, so I implore you to ask the following professor on the next slide. His name is Professor Coutinho. Our failure to understand the solutions to these questions is not due to an inability for such solutions to exist, but rather, as he would likely state, our failure to understand the solutions to these questions is due to an inability to translate the language of these solutions into a formulation humans can currently grasp. Of course, thank you for watching, but most importantly, thank you for considering Professor Coutinho's perspective.